In the realm of physics, the laws of motion stand as fundamental principles that describe how objects behave when forces act upon them. At the heart of this framework are Isaac Newton's first and second laws of motion, which he articulated in the late 17th century. Understanding these laws requires us to delve into the nature of force, motion, and the relationship between the two. Newton's first law of motion, often referred to as the law of inertia, states that an object at rest will remain at rest, and an object in motion will continue moving at a constant velocity unless acted upon by a net external force. This principle highlights a crucial aspect of motion, the natural tendency of objects to resist changes in their state of motion. Imagine a soccer ball sitting on a field. It will not move unless someone kicks it. That kick is the external force that changes its state from rest to motion. Similarly, once the ball is in motion, it will keep rolling across the grass until friction, another force, slows it down and eventually brings it to a stop. This illustrates the idea of inertia, where the ball's resistance to change is directly related to its mass. The greater the mass, the greater the inertia, and thus, the more force is required to change its motion. Now, let's transition to Newton's second law of motion, which provides a deeper understanding of how forces affect motion. This law states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. In mathematical terms, this is expressed as F equal ma, where F represents the net force, m is the mass, and a is the acceleration. This relationship reveals that if you want to accelerate an object, you must apply a force, and the amount of acceleration produced will depend on both the magnitude of that force and the mass of the object. To illustrate this, consider two vehicles, a small car and a large truck. If both vehicles are subjected to the same force, say a strong push from behind, the car will accelerate more quickly than the truck. This is because the truck, having a larger mass, requires more force to achieve the same acceleration. If we push both vehicles with a force of 1,000 newtons, and the car has a mass of 1,000 kilograms, while the truck has a mass of 3,000 kilograms, the car will accelerate at a rate of 1 meter per second squared, while the truck will only accelerate at 1/3 of that rate, approximately 0.33 meters per second squared. This example demonstrates how acceleration is not just about the force applied, but also about the mass of the object being acted upon. Furthermore, the implications of these laws extend beyond simple examples. In sports, for instance, a sprinter uses the principles of force and acceleration to improve their performance. By exerting greater force against the ground with each push-off, they can accelerate faster and reach higher speeds. Conversely, in a vehicle, understanding the balance of force and mass can lead to better fuel efficiency and performance. Lighter cars require less force to accelerate, making them quicker and often more economical. In summary, Newton's first and second laws of motion provide a comprehensive framework for understanding the dynamics of motion. They reveal that a force is essential to change an object's motion, and that the resulting acceleration is a direct consequence of how much force is applied and the mass of the object. As we navigate through various aspects of life, from driving cars to playing sports, these laws govern our interactions with the physical world, reminding us of the intricate balance between force, mass, and motion. They are not merely abstract concepts. They are the very principles that underpin our understanding of how things move.